This is lecture number 27 of the course AU 203 Statistics and Quality Control. In this lecture, we will talk about interval estimates and the confidence interval, which is another name for interval estimates. And then we will look into the confidence interval for mean value when your population standard deviation is known. And we will go into the one sample z-test, and we will look into the sample size concept. So point estimate is a single number which we have already seen in the previous lecture, which is a best value and which does not but this point estimate value doesn't provide information about how accurate and precise this estimation is. So this is one of the issue with the point estimate. As we already know that and this point estimation, the accuracy increases because the variance is decreased within the samples once you take a large samples. But still, this point estimate is for a given sample where the population parameter to be estimated, and there is a variability associated. Okay, let's see, for example, the concept of interval estimate means you're not interested in one particular value, but you're interested in the range of values. You have some data from a sample, and so for example, in this interval, the range is from 0.4 to 0.47. So our expectation is the likelihood of your parameter estimation. Your parameter would lying in that interval. So that is actually the idea about interval estimates. So from your population, you pick some samples, and from this sample data, you do certain calculations or certain formula, which actually allows you to come up with these numbers called 0.42, in this example 0.47. So we can, with some confidence level, we can say that there is a likelihood that the population parameter would be lying in that interval. So this process is actually called as interval estimation. So we call interval estimation is refers to providing a range of values based on the sample data, to which form an interval where your parameter, which is always an unknown, and parameter is always from a population, is expected to lie. And keep in mind, these intervals, these ranges are always drawn from a sample, so they would act as an estimator for those population parameters. And you can have this analogy for a game of ring toss. So here this pack, which is your target point, is your parameter which you are trying to estimate, and you have rings. So rings provide you a different range. So the diameter of the ring would be an interval where your expected parameter may lie. So you throw those rings and you expect that the true value of the parameter would be lying in that interval. So this is the analogy we have to look into interval estimate. As we know that interval estimator is actually taken based on the samples, which is actually a formula or a strategy which actually allows us to calculate that range of data points which represent certain interval. And the actual value of that interval estimator is actually the called an interval estimate. So there is the same thing, the concept of point estimation process, point estimator and point estimate. So the same thing lies with interval estimation process, interval estimator, which is from a sample data, and the which is actually some formula or some strategy which allows to calculate the interval and the value of particular value of that interval. These numbers, the data points, would be called as an interval estimates, and sometimes these interval estimates are also called as confidence interval. And once we will see in the mini tab, we will better understand what does it the estimators are, what the estimates are. So formally we call it an interval estimate, which is actually always coming from a sample. And this estimate is the target is to predict the population parameter, and we always use a Greek letter to represent a population parameter. So our interval estimates would be certain range. So there is some lower limit, there is some upper limit. So theta cap, whenever you put a cap, it is always an estimate. So L is representing the lower bound and U is representing the upper bound. And so for the statistic, which is always a capital letter with a cap on it, so that is always taken from a sample, and or it could be from some sampling distribution. So theta could be our unknown parameter, and we expect that from our statistics that theta would with certain confidence we can say that theta is going to lie between that interval theta L and theta U. So that is these values of those numbers which forms the interval are actually called as interval estimate. So we can see that theta is our parameter, and we expect in that several intervals from each sample. Theta L would be its lower limit, theta U would be upper limit, and you can see here all these intervals are of same size, but it could be of different lengths depending upon the sample data. So all these different samples would actually bring different values of the statistic. And from some formula we calculate the lower and upper limits. So these n intervals would be for different for every sample, it would be different. So we can think of all these to be as random variables. As we already have seen that once your estimators, so your estimators are always from a sample, and they can vary from sample to sample. So all these estimators would be itself would be a random variable. Okay, so the idea behind confidence interval we will look into after doing it in this mini tab. I'm trying to open it a mini tab now. So in mini tab, let's say we first generate some data. We call it X is a population, and how to calculate random data from normal distribution. Let's say this time I calculate 1000 rows that has to be generated and stored in column 1. Let's say my mean value is 100 and my standard deviation is let's say 5. So once I do that, I can see that I have generated 1000 rows here where mean value is 100. So if you look at the column statistics of this population, let's say I'm interested in calculating column statistics, so I'm interested in its mean value. So and variable is X here. So I can see 99.9929 is its mean value. So its nominal value was 100 and standard deviation was 5, but still that its mean value is 99.9. Okay, what I'm going to do now is to generate samples. Let's say X1 is my sample, and how to generate a sample from this column is going to this column and random data, and go on to the top sample from column. So from sample from column, let's say I generate a sample of 35 rows, let's say, and from this column CX1 and stored it in X1. So, and I'm just sample with replacement means every time you have 35 sample elements available, and once we pick it, when we return it back. So once I do this, I am able to generate 35 samples here. So 35 elements have been taken from this population column X. So X1 would be my first sample. Let's say I generate another sample in the same manner and calculate the random data from sample from the column, and this time also with the same sample size of 35 with replacement. So I got it this. Let's say X3 is another, or X4 is another. I don't know, we can do it automatically, but we do it one by one. Let's say we have a random data from sample from this column, and here this time is X3, and this time is X4. I just call it an X4. So fourth sample is generated, and this time again the fifth sample is generated. Let's say I'm just generating 5 samples, and so you can see that 5 samples have been generated with 35 sample size from this population X. So X is my normal population, as I already mentioned it. I have with the mean of 100 and standard deviation of 5, and out of that randomly selected 35 elements from that population. What I'm going to do now is to graph an interval plot. So here it is an interval plot, and this time I want I'm sorry, not samples, but not help, but these samples, multiple samples, and from X1 to X5 I selected, and here I just go on OK. So I can see that there are several samples. X1 is my first sample, its mean value is close to 99, and what I can see now is to add another line. I call it a reference line at my mean value of 100. Actually 100 is my mean value. So you see, I mean, this sample 4 was luckily just within this interval marginally. So you have 5 different samples with 5 different intervals, and this would be, let's say, the interval values, interval estimates actually. These 96.7 or 101.2 are these values which are lower limit and upper limit. And here my sample size was 35, and with 95% confidence interval I can say that my true mean, which is 100, lying within this interval. So, and you see in 5 these samples, all of them are lying within this interval, but this X4 is just about to leave. So what we can say, if we have 20 such samples, and 95% of 20 would be 19 samples would be lying within this interval. One is likely that it could be either above this 100 line or below this 100 line. So it is the true mean is not lying in that. So that is actually your interval estimates, and keep in mind each sample means are not 100 actually, even though we have taken a population, samples are drawn from a population which is normally distributed with mean 100, but all these samples would have different, so this would be your mean distribution. So different values are going to come with 2 are above 100 and 3 values out of 5 are below 100. So there is a distribution of the sample mean as well. So we will look formally into this after doing it in Minitab. Looks at it. Okay, so what is confidence interval is actually the range of values which you that are derived from your sample. We call it in statistics. That is likely to contain the value of an unknown population parameter, which is what we have seen in this previous example, the mean value. So confidence intervals we have already drawn, and from this random nature of the confidence interval, we have seen that from different samples even though each samples of same size is taken from the same population, but the lower limit and upper limit of each interval would be different. So it is likely with 95% confidence we can say that the true mean of the population parameter is going to lie within these sample intervals. So the percentage of this confidence intervals that contain the parameter is actually called as confidence level or degree of confidence. For example, in this previous what we have seen in the Minitab is 95% is the degree of confidence. So creating this confidence interval is just like the same as throwing net over a mean value or target value. And all these confidence intervals would be random variables itself, because their lower limits and maximum limit for each sample could be any value. So its location and its variance is itself is random in nature. For example, in this plot, I have confidence intervals have been plotted and interval plots, and you can see out of 21, one is the red one, which is not their lower limit, and their lower limit and their upper limit is not, the true mean is not lying in that interval. So this black line is representing the true mean, and these blue lines are your confidence intervals. And we can see one of the confidence interval might be likely to be not containing the population parameter, which is we have seen in this previous example as well. But we have just plotted 5 samples, but if you will do this same 20 times, so you expected at least one could be not having in this interval. So this is all random in nature. And there are a lot of examples. For example, you are a spark plug manufacturer and you are interested in the variability in their spark plug gap. So you have taken a random sample of 100 different spark plugs and measure the gaps in millimeters. So your point estimate would be your population mean, and your standard deviation and if you take the samples, obviously in each samples your sample means have been evaluated that come out to be 9.275 and 1.93 millimeters respectively. So once we create a confidence interval for one of the confidence interval is where lower limit is 8.89 and upper limit is 9.66, and we can say that its true mean, which is 9.275, which might lie in that interval. So we can see that the mean value was 9.275. So this would be the point estimate, and this something around 8.89 and around 9.66 something is their upper limit. And so with 95% confidence, then you can say that your from different samples your mean value would be lying in that interval. So we have only taken a one sample. You can take different samples generating different lower and upper limits. Okay, now we can formalize the same thing. Let's say for a sampling distribution of theta cap. Theta cap is always an estimator, which is based upon the sample. So from that estimator, from that sample estimator, there is certain formula by which we will generate the lower and upper limit. And we can see that there is a probability associated that your population parameter theta would be lying between this estimate is some there is certain probability associated. And we can see that for instance theta L is the lower limit, theta U is the upper limit, and this small letter representing the estimate of that estimator. Capital theta L is an estimator for the lower limit, and its value is theta L. So for every sample this theta L value would be different. So theta L in general is a rule by which we can or a formula or a strategy by which we could have the estimate of that estimator. And the lower limit value of the small theta cap L would be representing the value of the estimator, which is actually called an estimate. So let's say if their probability is 1 minus alpha, and alpha can range between 0 to 1. So we have a probability that the true mean or the population parameter is going to lie in that interval, come out to be a probability of 1 minus alpha. So if alpha is 0.05, then 1 minus alpha would be 0.95. So 95% is the probability that the true mean would be lying in that interval. So an interval estimate for this population parameter is also known as a confidence interval. So these are all different confidence intervals we have generated from different samples. These intervals is obviously computed from those different samples, and this 100 into 1 minus percentage would be the confidence level, and this 1 minus alpha is actually represent, we call it a degree of confidence, and these theta L and theta U are actually the lower and upper limit of that confidence interval. So here we have information about the precision of the estimation. So with what certainty we can say that, with what probability we can say that in this sampling process the true mean or the population parameter is going to lie within those intervals. We already know about what the different lengths for these intervals. We know it depends on to the size of the sample as well. We have earlier seen that we have 5 samples of the same same size, but if we could have one sample could be of 35, or one could be of 55, or one could be of 100 elements in the sample. So obviously their interval, their lower and upper limit values would be depending on the sample size, and we will see it later as well. So in a nutshell, the confidence intervals are actually created for estimating the parameters. Parameters are always from a population. So confidence intervals is actually something which always an estimator, and their values, particular values of those estimators are called estimates. So these confidence intervals are always generated from the statistics. Statistics always dealing with the samples, whereas parameters are always dealing with the populations. Okay, if you look at this particular example, you have the spark plug manufacturer where you have some lower limits and upper limit. Okay, so this is actually an MCQ or a problem in which of the following statement is or are true. So this is something you have to work out. So a spark plug manufacturer is studying a problem of too much variability in the spark plug gap. Take a random sample of 100 spark plugs and measure the gap in millimeters. Below is actually a confidence interval for mean gap of a spark plug with a confidence level of or degree of confidence or confidence level of 95%. It means alpha value would be 0.05 because 1 minus alpha would be a degree of confidence. So and their lower and upper limit comes out to be, we will see how to calculate, but let's say they are available right now 8.89 and 9.96, and true mean is For that, the sample is lying here, the sample mean is lying here, whereas the true mean would be some other value, but the sample mean is actually showing here in these interval estimates, the lower limits and upper limit. Okay, which option is correct? Just explore, take a pause and try to answer that question. As you see, 95% of spark plug manufactured here would have their gap lies between. So if this information is not represented from this confidence interval, because as we know that this would be something a random value. So A cannot be correct option. We can be 95% confidence that the sample mean of the spark plug lies between 8.89 and so it is about we can be 95% confidence. So that is also not the idea of the 95% confidence. We can be 95% confident that the population mean of the spark plug lies within. So we can be 95% confident the population mean. So as you know, this interval estimate is actually not related with samples. Here you're talking about population mean. So of the spark plug lies between this. So we cannot be confident. Third part, in repeating the sample 19 out of 20 times, that is 95% of the 95 confidence intervals would be able to capture the true mean of the spark plug. So third is actually the D1, the last one is actually the correct answer. This statement is true because we are saying that in repeated sampling we can only say that the degree of confidence is 95%, that we are able to capture with 95% confidence that the true mean would be lying in that sample, would be in that interval. So this is the idea about confidence interval. Okay, now let's look into finding out how to find out those confidence intervals for mean values in first case when your population standard deviation is known. So here you put a random sample of size and independent observations from a normally distributed population with mean mu, which is obviously the mean value is unknown, but the standard deviation here is known. So you know the standard deviation of the population. So confidence interval can be thought of as some point estimate, which is your sample mean. Some point estimate is your sample mean plus minus some margin of error. So if you have these two informations, you can work out the confidence interval. So mu is a population parameter and x bar is your sample mean, which is actually a point estimates. Estimates are estimators, point estimator actually, sample mean is a point estimator. So the value of that point estimator is actually called as point estimate. So if you calculate some number, that would be the point estimate, but this would be your point estimator. And if you know this margin of error, you can generate a confidence interval. So as we know that here a random sample of n is choosing, and we have information that the population is normally distributed. So this point estimate, which is a sample mean, we can say that it is also normally distributed with mean and variance, and we know without replacement case in which sigma square over n is your variance. So once we do this standardization of to turn this x bar variable into z variable, and if you want to see the distribution of the z, so there is a z value. We can see these limits are generated on the basis that 1 minus alpha is a probability, and with let's say if this is a 95% area, then alpha would be having a value of 0.05. So 1 minus alpha would be 0.95. If this shaded area is 0.95, then the white area total together is actually 5% area. So This would be alpha by 2, so alpha is 0.05, so it would be 0.05 upon 2. So 0.025 and 0.025, that would be that area. If you sum up that area, it would be 5% area. So the corresponding value of Z for this would be defining your margin of error, and we will see it how. As we already know that Z itself would be a random variable, and the probability of getting a Z would be in this range from minus Z alpha by 2 to plus alpha by 2. Is this probability is 1 minus alpha. So just Z is replaced from this standardized score, and then the same expression I'm right now, because I have here sigma over under root n, so I'm multiplying both sides of this inequality with sigma over under root n. So once you multiply here, this cancels out, so you end up with sigma over under root n and sigma over under root n here. So here it is the sample mean value, how it differs with the true mean. So here simplification to be done, subtract x bar from each term of inequality. So as we know, we are interested in subtracting plus x bar and minus x bar. So here it cancels out, so you get negative x here, negative x bar here, and then you need to change the divide by 1, so its inequality changes. So we can say that the true mean would be lying between this and this value. So you can say that your true mean would be lying, so this would be your point estimate, and this would be your error, standard error, and your sample mean would be lying in that range with this degree of confidence, 1 minus alpha degree of confidence. So your confidence interval would be x bar plus minus Z value of at alpha by 2 times sigma over under root n. So this would this would be sometimes called as standardized error. So the point estimate, which is a sample mean plus minus standardized error, would this is a rule actually, or a formula which allows us to calculate that estimate of confidence interval. And with 95% confidence, you can say that your true mean would be lying in that confidence interval. So that is what we have worked out. So we have a random sample of n is selected from a population where we already have seen that the variance is known and their sample mean is computed, and we can say that this is the degree of confidence. For example, if alpha is 5%, alpha is 0.05, then 1 minus 0.05 would be 0.95. So we can say with 95% confidence intervals, most of the time we used to pick a value of 95% confidence. That's why I'm always picking alpha to be 0.05, but it can take any value alpha. You can take 4%, you can take 3%, you can take 9%. So it could be any value, but I'm just here picking it a 5% alpha to be 0.05. Okay, so we learn to calculate the interval estimator, which is a formula to calculate the estimate, interval estimate, so that you know the interval. Let's say if x bar is your estimator, value of the estimator which lies in that interval, and this is sometimes called as a margin of error, or sometimes called as standardized error. So your sample mean would be lying in that interval. So if x bar is used as an estimate of your population parameter with 95% confidence, or 100 into 1 minus alpha in general case, that error will not exceed a specific amount when the sample size is this. So just turn this interval standardized error into a formula for sample size, because if it is away from the sample mean with the distance e on this side and distance e on this side, or what we call it error e, then your sample size can be computed using this formula. So this is actually same from that this thing is coming, just multiplying, taking a square, and you will be able to get this expression. At a given confidence level, with this margin of error is increasing, so we have seen this as your E is some bigger number, so smaller sample size would be needed. If E is a shorter range, then sample size would be larger. So for a given variance, because variance of the population, standard deviation of the population is actually known. So just depending upon the degree of confidence, you can work out the value of Z alpha by 2, which is for standard normal distribution, it is 1.96. So if you know this 1.96 multiplied by the known standard deviation and the error, you will be able to calculate the sample size. Okay, so just generalize if a minor, this term is the lower limit, this one is an upper limit, and you can write the lower bound and the upper bound, and we can say that your true mean would be, because it is an interval which is bounded between the two limits, or if this could be greater than this or less than this, it could be left bounded, it could be right bounded. So in general, we can say that your confidence interval formula is your estimate of mu, which is actually a point estimate. It could be any estimator, plus minus some critical value. For example, Z alpha by 2 is some critical value depending upon the degree of confidence, times the sigma over under root n. Here sigma over under root n would be your standard error. So this would be the formula for calculating the confidence interval. Okay, let's see the problem we can solve for one sample Z test. Let's say we have the data given for 10 measurements in which impact energy on a specimen is noted, and the values are, these 10 observations are the impact energy in joules, and we know this sample is taken from a normal distribution with the known value of standard deviation, and we need to calculate a confidence interval for this mean impact energy. So the first thing is always define, let x be our impact energy, which is normally distributed with unknown mean and population mean, and its variance is known here. So for that sample size 10, we know the sample mean, just add them together, divided by 10 to get the sample mean, and with 95% confidence means 1 minus alpha is 0.95, then alpha would be 0.05, then 1/2 test, because we are interested in calculating the confidence interval where in this range where the critical value is 1.96. So you can get it from the standard normal table. So formula for calculating the confidence interval is the sample mean plus minus the critical value times the standard error, and we know sigma 1 is known and n is 10. So substitute the values to get your required interval, and the same thing we can do it on a Minitab, and I will show you its box plot as well as its confidence interval. So how we can do it in a Minitab? Let's say the data given here, the impact energy in joules represented by first column, the data is given in this first column, and we need to calculate the confidence interval for that. So what I can do is I go on to the stats tab, basic statistics, and one sample Z test. If I just click on that, here my variable is this I selected here, and x to be selected here, and forget about this older value. So x is that selected, and standard deviation, as I know, is 1, and in this option it is right now forget about, and I am interested in the box plot, so just click on box plot. So if I do this, I can see that here in the session window Uh, for the known standard deviation, which is 1, this sample of 10 sample size, the mean value is 64.46, and the confidence interval, the lower limit is 63.84 and 65.80, and this is what we can see it in this box plot as well. So the lower limit is this, and which is 63.84, and upper limit is 65.08, which we have seen a very large interval for this data, and you can see the lower value of this and maximum value of this, the median value, lower quartile and upper quartile, that is actually the box plot. So this confidence interval says that their standard their mean value, which is an unknown for the population, 95% of the times it is going to lie in that interval, which lower value is this and the upper value is this. So it is simple, by which very simply we can draw it in a Minitab. Okay, now go into the second case in which you have your population derivation is unknown, but your sample size is greater than 30. So what we can do is we can estimate the confidence interval just using this formula, in which instead of population standard deviation, you have a sample standard deviation. So in general, confidence interval is a point estimator, which is a sample mean here plus minus the critical value, which is Z alpha by 2, and this is standard error, which is S over N. And if you look at this problem in which you have 53 concentration for mercury in a fish sample of 53 fish, the mercury concentration is noted. So these 53 data points are given. Okay, here you see the sample size is greater than 30, and population standard deviation is an unknown. So first thing is we need to look into whether this distribution is normal or not normal. So we need to draw the probability plot and the histogram. So, and then we need to calculate the confidence interval for this mean concentration. So the first step is to draw the probability plot and the histogram. Histogram, you know how to draw it from this data point. I will show you today this probability plot. So in this probability plot, if you go onto that, for calculating in the graph, there is an option of probability plot. So this is actually a probability plot test whether your data follow a particular distribution or not. So for example, if I just click on that, I have a single data point, let's say the concentration of mercury. So this concentration of mercury I have selected here, and I'm testing it whether it is a normal or not with unknown mean and standard deviation. So just go on that. So I will be able to come up with a plot. I call it a probability plot, and you can identify it because the percentile is given here. So and on this horizontal axis you have been given a concentration. So average concentration is 0.5 to 5 parts per million, and standard deviation is 0.3486. So this is from 53 samples that has been investigated, and you can see this middle line is, if the data, all the data points are lying on the middle line, then it can be considered as a normal distribution. So you can see so several of the points are away from the center line, and some are even outside this interval, which has been drawn using the 95% significance level, or 5% significance level, and 1 minus alpha would be 95% in this case. So we can draw this probability plot. So this probability plot help us because it doesn't look, because data is not on the line, so we cannot consider it to be a normal distribution. But even though it's not a normal distribution, but we will use this one sample Z test to estimate the confidence interval for its mean, because here it's not a normal distribution and its sigma is unknown. So but the sample size is large, so at 95% level the critical value is 1.96. so from this descriptive statistics you can see its mean value and standard deviation and minimum and maximum value of this particular concentration of mercury, and confidence interval can be drawn using this, where because the sigma is unknown, so we are using a sample standard deviation to be used in calculating the confidence interval. So you calculate the confidence interval, which comes out to be 0.4311 and 0.6189. So, and using this one sample test or one sample Z test, you can get this confidence interval with lower limit and the upper limit. So this is how, and let's see how to do it on a Minitab. It's quite simple. What I need to do is go onto the stats bar, basic statistics, one sample Z test. So here I need to perform a Z test where the data is given is column 2, which is a mercury concentration, and known, this is not known, but 0.3486 we know from our sample. So I just put the same thing, that sample, and the graph I want a box plot, let's say. So I can see okay, this 0.3486, before going into that we need to go into the checking out its descriptive statistics for this data point. So let's say these values I'm interested in knowing that. So I can see the 53 sample size, 0.52 mean, and standard deviation is 0.3486. So we need to do this descriptive statistics before going into the finding out the confidence interval, and then I need to go into this basic stats and one sample Z test, and here I'm using this my and 0.3486 is standard deviation is known to me, and with 95% confidence level, and I just need a box plot. So okay, if I click on that, I can see that 0.4311 and 0.6188, and you can see it's 0.34311. It's quite a short confidence interval, because if your sample size is large, then the width of the confidence interval is very short, because your sample size is fairly large. So that's why you can see your mean value is this, your standard deviation is this, and your confidence interval is this. So very quickly we can do it, and we can see the box plot as well as confidence interval. And keep in mind this confidence interval, because lower limit is 0.43, it is different from if you just plot the data, not doing the sample statistics. For example, if I just go on graph and trying to plot the interval plot, for example, for this particular data, let's say this one is, I have selected it, and I just select that, and I can draw this interval plot, which is not the same as 0.42 and 0.262. These limits are different, because here it is not performing a one sample Z test. It is not doing that. It is just plotting the data in this column. So it is totally different from this interval. This interval plot is not the same as the confidence intervals, even though it is just writing down that, because here we haven't provided any information about the population standard deviation. So what these are different values, so don't be confused with the one sample Z test. So what you need is to do, in order to get the confidence interval, here is go to this basic stats, one sample Z test, and here you need to do this. So here you are going to get the confidence interval, which is and the value would be 0.4311, which is different from just in an interval plot. So here you are using a Z test. Your test statistics is a Z test. Okay, the last problem in this lecture is this for calculating the sample size. Here the mean is unknown and standard deviation is 1.3, and the 95% confidence level, and we need to look for the number of sample size in order to achieve the confidence interval such that our mean is less than with the total width is less than 2 units. So this is something less than 2 units, and we can do it using in the Minitab. Just go on to the stats tab, power and sample sizes, and here pick a sample size for an estimation. So because the parameter of interest is a mean, which is normally normal distribution, and we are interested in its 1.3 is given here, is the 1.3 is the standard deviation, and the total width is 2, so E comes out to be 1. Margin of error is twice of E is 2, then E would be 1, and standard deviation is 1.3. And in this option I need to choose less than this, so I need to choose this lower bound and just click OK. So I'm going to get this sample size of 7, which you have seen that we have done it manually just by assuming that there is a population which is normally distributed with unknown mean and standard deviation of 1.3. So we know the formula for calculating the sample size, and here 2E is equals to 2, width should be less than 2, then E should be less than 1, and just substitute E less than 1, then N comes out to be 6.49. So N should be at least 7. So this is how we have done it using the formula, and the same we have used Minitab to calculate the same. This is where I stop this lecture.